speaker is Nick Murphy, and he's an astrophysicist at the Center for Astrophysics in Cambridge, Mass. And he attended the University of Michigan as an undergraduate and then went to graduate school at University of Wisconsin in astronomy. So Nick began believing in open source software while he was still a student. And even as far, this is kind of neat, he went as far as including Fortran subroutines in an appendix of his thesis. Good man. So Nick has been at the Center for Astrophysics for the last decade, and he worked largely on magnetic reconnection and solar eruptions. Nick was a co-organizer of the Inclusive Astronomy 2015 conference and co-founded the American Astronomical Society's working group on accessibility and disability, and is now a member of the APS-DPP Diversity, Equity, and Inclusion Organizing Collective Committee. So over the last few years, Nick's been a core contributor to Plasma Pi, which is an open source software package for plasma research and education. And I can just tell you, parents, Nick, they really feel that the area of astrophysics is more inclusive than, say, the area of fusion plasmas. It's interesting. So maybe the work you're doing is having some effect. I don't know.
It's a lot of us working
Anyway,
on
go
it.
ahead.
All right. Yeah, thank you for the kind introduction. And I'm grateful for the chance to talk about how, as a community, we can make plasma science more open and reproducible. So when I was putting these slides together, I had to decide between two different approaches. Should I talk about small scale stuff, like how we can make individual research projects reproducible, or go more large scale and talk about how we can make plasma science and fusion energy sciences as a whole more open and reproducible? And I decided to go with the large scale approach because there are a lot of community-wide barriers to open science that limit our ability to make individual research projects reproducible. So, and then of course, I'd also have a whole bunch of people to thank, more than I can take time to say now, but I'd especially like to thank members of the Plasma Pi community and co-organizers and participants of Tech Week 2021. Right, so
Nick, can I stop you for a sec? We have a few requests to turn on to turn a bit up your microphone volume.
Okay.
Good. Thanks.
How's this?
Yeah, it's perfect.
Okay, cool. All right, so Paul did introduce me. I can go over this a little bit again. I went to grad school at the University of Wisconsin in Madison, and I did my thesis connecting laboratory and astrophysical plasma physics, so pretty interdisciplinary, mostly focusing on magnetic reconnection. And then after that, I came to the Center for Astrophysics as a postdoc and was able to get a research position here after that. And I've been working kind of at the interface between solar physics and fundamental plasma science. And then more recently, in the last couple of years, I've been a core contributor to Plasma Pi and also spending a lot of time advocating for open and reproducible plasma science. And I also have a couple of pandemic, I'm not sure if hobbies is quite the right word, but I've spent a lot of time reading tokamak data management plans, which is a range of emotions, and then also singing about open metadata standards. The syllable pattern works with both Strawberry Fields Forever and the theme to the Teenage Mutant Ninja Turtles cartoon in the 1980s. So very versatile. All right. So to give a bit of background beyond plasma science, I can mention the reproducibility project psychology. So reproducibility is foundational to the scientific method. And if we want to be able to reproduce, if we want to be able to believe results, we should be able to reproduce them, to be able to replicate them. And the reproducibility project for psychology was an attempt to replicate results from 100 journal articles. And unfortunately, only 39% of the results were successfully replicated to the same statistical significance. And then there have been similar meta studies that show replication rates that usually range from 1/3 to 2/3. But that's still a lot less than we would like it to be. And the inability to replicate roughly half of published results has been dubbed the reproducibility crisis of modern science. So let's define reproducibility and replicability. So reproducibility is when you are able to get consistent results when you use the same input data, computational steps, methods, and code, and conditions of analysis. So you're able to reproduce the results with code that has already been written and data that has already been collected. Replicability, on the other hand, is making sure you're able to get consistent results across studies aimed at the same scientific question. So it's using independent data to get the same conclusions, and both are really important. So important question to ask is, how reproducible is plasma science? Like, how reproducible are fusion energy sciences? And unfortunately, there haven't been any meta studies performed to gauge how replicable results are from plasma science, from fusion energy sciences. So we don't really know how reproducible plasma science actually is. But unfortunately, a lot of the sources of irreproducibility that exist in other fields are present for us also, both in plasma science and fusion energy sciences. And one of them is hypothesizing after the results are known, which is also called harking. And what harking is when you pass off a post hoc hypothesis, a hypothesis that you come up with after doing the study, and you treat it as an a priori hypothesis. So presenting it as something that you were trying to test before you actually did the study. So an example of this is we have a hypothesis and we design an experiment to test it. When we finish the experiment, we find that the data don't match the hypothesis. And instead of presenting that result, we create a new hypothesis that we designed to match the data. And the problem with this is that it leads to excess false positive results. And it also leads to hypotheses that are always confirmed, which is a little bit strange. And we also lose information about what the original hypothesis actually was. So what was our thought process going into the study? So it's important to state original hypotheses, and we can also specify if research is exploratory or confirmatory. So exploratory research is one where we're seeing what's out there. And confirmatory research is that if someone has done, for example, exploratory research before, we're taking the time to confirm their results. And apologies if there's some construction sound in the background. There was a plumbing urgent situation upstairs. So, right. Another source of irreproducibility is data dredging, and that also leads to false positive results. Data dredging is when we perform a whole bunch of statistical tests and then selectively report the ones that are statistically significant, that have a probability of, for example, greater than 5%. Sorry, that I'm getting that wrong. That the chance that, how to describe it? that there's a 5% chance that the null hypothesis is true. So for an example of this is that we have a multivariate data set and we test for correlations between every variable combination. And then we report the statistically significant trends. So we find a whole bunch of research through a whole bunch of possible correlations and then report on the correlations that exist. But the reason why this isn't the best practice is that some correlations will happen just by random chance. And if we selectively report only the correlations that happen, we're not taking into account the probability that they did happen by random chance. So we're essentially hacking the p-value. And it's better to come up with a hypothesis beforehand. And as we do studies that look for potential correlations, it's still important to report them, but we should treat them as hypotheses for future work. And this is something that is important to keep in mind when doing data science research. Another source of false positives is publication bias. And that happens because as a community, we value positive results more than negative results. And positive results are more exciting. They're easier to get published, especially in a high impact factor journal. And they end up being better for our careers. On the other hand, null results are less exciting. That's how we tend to think about it. They end up being harder to publish, and they end up being quasi-neutral for our careers. We might be able to add a publication, but it probably won't get cited much. And also highly undervalued. Null results are an important part of the scientific record. So a way that other fields are handling this is when their journals have policies that say that null results are acceptable. And I haven't noticed any plasma journals that specifically say this. And another alternative would be to pre-register research plans. So something that's happening more and more frequently in social sciences is that the research methodology gets pre-registered with a journal. So they submit the methodology. And if the methodology gets approved, then they're guaranteed to be able to publish the result, even if it ends up being a null result. So one thing that I was curious about trying, and I'm not sure how this will actually work out, is a crowdsourcing experiment. So I'd be curious if any of you know of a plasma research paper that explicitly states a hypothesis and then shows that the hypothesis is not supported by the available evidence. So essentially, plasma research papers that conclude with null results. So feel free to post that on Discord in the Open Plasma Science channel. And I'm not sure how to interpret this completely, but it was something that I was very interested in trying. All right, so can take a moment to ask if there are any questions or comments.
Yeah, if you check the Discord channel, we have a couple of questions about the first one from Cameron. How do other subfields of physics do in terms of reproducibility?
Oh, that's a good question. Last time I checked, there had not been any meta studies performed in other fields of physics either, or astronomy. One thing that is common is that physicists tend to have more confidence that the results are reproducible, though that doesn't necessarily mean that the results actually are reproducible. But it's hard to say because these meta studies have not been done.
Gotcha. And then we have another question from Greg Wallace. And now I don't know what this refers to, but does this imply that the new hypothesis should not be tested or stated, or just stated in combination with the original hypothesis? Greg, do you want to comment on about which
Sure.
point in the presentation?
It was in reference to your sort of suggestions that you not create an ad hoc hypothesis a posteriori. And I guess the question was, do you state both the old hypothesis and the new hypothesis, or just state the old hypothesis and never ever come up with or never talk about a new hypothesis when you publish?
What I would do is state the old hypothesis and then present the new hypothesis as something that is consistent with the data, but be sure to mention that it was come up with after the study was done and that it needs to be confirmed by new experiments. So the problem happens when we pretend that a hypothesis was formulated before we did the experiment when it was actually formulated after. But if we're open about when we came up with that potential interpretation, then that greatly reduces the problem.
Thank you.
Sure. Were there any more questions?
Yeah, so, okay, general comments about not knowing about studies that actually, state negative results or that kind of, that kind of topics. And we have a comment then from Marisa about people also intentionally avoiding things that should be common knowledge that they know and use that are problematic, and publish things using those things anyways. And then I think Andrew is asking a question: what would be your prior? What would your prior be on % of plasma studies that are not reproducible? I'm curious on what your expectations of the scale of the problem as someone who's been thinking about this problem.
Oh, that's really difficult. It's a little bit tricky also because in the social sciences, there tends to be a lot more care with statistics and how those are handled compared to plasma research from the subfields that I've been a part of. And I think I would expect that plasma science would be consistent with the other fields that have done these meta studies. So I would also guess that maybe.
Nick, I have a.
Oh, go ahead.
Yeah, Nick, this is Paul. Regarding this reproducibility in plasma science, so you could have a lot of smaller plasma science, plasma physics experiments, let's say. But if you're talking about comparing experimental results, for example, on big tokamaks, oftentimes you can't really do the exact same experiment or make the same measurements on two different devices.
Right.
How much is that different in plasma science than, say, in psychology? Maybe you can do the exact. Is it easier in some of these other sciences to do the exact same experiment?
Yes. In psychology, it was a lot easier to do the same experiment. To do something like the reproducibility project in plasma science, that would be a lot more expensive. This does remind me of one editorial that we don't necessarily need to replicate the result using the same experimental method, but maybe test the same hypothesis, but from a different angle. So essentially triangulating on getting the scientific results. But yet,
Maybe have the same physics result, but it isn't the exact same experiment you did to get that.
yeah. So
Or-
it's,
Yeah,
yeah,
okay.
there are a lot of differences between fusion energy sciences and social sciences. All right, were there more questions or shall I go ahead?
No, you can go ahead. Thanks.
Okay, cool. All right. So now that we've talked about scientific reproducibility, we can go into a bit more depth about open science, which is a bit, well, quite a bit broader than scientific reproducibility. So the goal of open science is to ensure the free availability and usability of scholarly publications, data from scholarly research, and methodologies. And that includes making codes open source as well as algorithms. And this definition is coming from a report by the National Academies on Open Science that was published a couple of years ago. And there's a lot of principles that are associated with open science, and the specific principles depend on who you ask. But ones that come up a lot are open access data, open source software, open methodology, open peer review, open access publications, and open educational resources. And the ones that I've worked most with are open access data and open source software. The one really interesting piece of news is that all journals from the American Astronomical Society are going to become completely open access on January 1st. So that was a bit of a surprise to me, but that is very good news. So, and if you just heard a car, I'm by a fairly busy intersection, so apologies for that too. And so why do we want science that is both open and reproducible? The most important reason in my view is that it reduces barriers to access, barriers to entry into the field. So if someone can access existing codes and data, then they would be able, it'd be easier to start out with doing something like archival research and gain entry to this field. Open science also broadens the research impact. Open access journal articles tend to be cited more often than closed access journal articles. And more people can access your scientific results. Open science also improves scientific reproducibility by making sure that the codes and data are openly available. Open science also, by definition, makes research more transparent, and it also makes publicly funded research available to the public, the people who are paying for it. And the combination of these 2 points helps improve trust in the scientific process among members of the public. Also, data from fusion experiments tends to be pretty expensive to get. And if we want to maximize the use of the data, we should make it openly available and put it in a form that makes it easy for people to work with. It also allows community review of results. It's pretty common in astronomy to make research openly available. And one example that you might have heard about a couple of years ago were the BICEP2 results, and they claim to have found evidence for gravitational waves in the cosmic microwave background. And after they made their results public, the broader astronomy community said, no, wait, these polarization signals were more likely caused by interstellar dust, so dusty plasmas in our own galaxy. And they were able to revise the results. And the whole process, they ended up doing science better by making it open. And open science, like open source software, and other aspects of open science are also investments in our future. But there are a lot of barriers to open and reproducible science that happen across academia, and also some things which are fairly specific to plasma science and related fields. So one very common one is that there is pressure to publish, and often that comes with a fear of being scooped, so you're less likely to make your data openly available. There's also a lot of time pressure that we need to get publications out the door, and it does take a time investment to make our research open. There's also some financial pressure. For example, that open access publications often cost extra. I think it might be like roughly 50% to twice as much more to publish an open access article than to publish a closed access article. And then also hiring software engineers, for example, or people to build databases, that also costs more money. There's also a lot of bureaucracy and institutional inertia, and I'm sure none of us have ever had to deal with any of that before. But it's one of the things that does impact our ability to do open science. And because if we think it's working as is, then there's less motivation to change. But the status quo, in a lot of ways, is broken. And one example of dealing with bureaucracy is that there are a lot of decisions that would need approval of the ITER Council for ITER's like data management plan and software policies and things like that. And that could require approval of all ITER member states. There are also power imbalances. So early career scientists tend to be more likely to support open science, and being early in a career makes it harder to affect change at larger scales. And another one which is really apparent in plasma science is toxic culture. And this can be things like blatant or subtle acts of racism, sexism, ableism, and so on. And things like bullying, harassment, and discrimination, and even cases of like retaliation. And that's something that we do need to change in order to have open science. And there are also equity gaps. So different access to resources at different institutions and among different groups. And there are also things like language barriers. So scientific information is sometimes only available in English, which makes it harder for people who don't speak English to access that information. And then in plasma science, there are also national security reasons and intellectual property rights, which there can be valid reasons to keep aspects of science closed, but all of this gets really complicated, so I can't say much more about it. A big problem is that in the academic reward system, it's set up so that what's good for science is not equal to what's good for scientists. So things that are good for our career are new and exciting results. And I've often heard from grad students who say that their advisors encourage them to not waste time making their data and software openly available, that it's better to get publications out the door. And as far as career advice goes, that is more likely to get you a job. But what's good for science is taking time to write software documentation, taking time to write tests, investing the time that's needed to make data and software openly available, and all sorts of things like that. And a question which I don't have the answer to is, how can we make what's good for science also what's good for scientists? And this is something that is not specific to plasma science, but something that that's affecting a whole bunch of different fields. So how do we get closer to open science? It is going to be a process. It is something that's going to take a long time and a lot of effort. One of the things that we need to do is to change our culture, and we want to be able to ensure psychological safety in our community, and we need to eliminate equity gaps. We also need to change our institutions, so things like promotion and tenure policies. So making sure that contributions to open science actually do get counted for that. And we also, as a community, need to collaborate on technical infrastructure. So things like open access data and open source software. And that's the part that I've been spending the most time on. And one of the graphics that has come up a whole bunch of times in doing diversity, equity, and inclusion work for plasma science is this one, which shows that a pyramid of things that we need. So we need psychological safety to get to moral courage. We need moral courage to be able to get to cultural competence. We need cultural competence to be able to get to a community that is inclusive, that is diverse and equitable. And then on top of that, we're ready for excellence and innovation and open science. And at the foundation of this is psychological safety. So psychological safety is absolutely necessary for open science. And what this means is that members of the plasma community should be able to be their authentic selves, to share their perspectives and make honest mistakes, and do this without fear of bullying, retribution, or discrimination. And psychological safety is foundational for diversity, equity, and inclusion. And diversity, equity, and inclusion are foundational for open science. And if you want to learn more, I highly recommend this paper by Kimberly Young McLear and collaborators. More specifically to scientific collaborations and open source software projects, it's really important to have a code of conduct. And every collaboration with more than one person should have a code of conduct. And this code of conduct should not only describe unacceptable behaviors like harassment and bullying, but also promote positive behaviors like demonstrating empathy, behaviors that do promote psychological safety. And it's also important that each code of conduct have an enforcement policy. And one example that's emerging as a standard in the open source community is the Contributor Covenant Code of Conduct. And I think that is the code of conduct for this meeting also. So please correct me if I'm wrong. So, and there's the website for that. Okay, so here's another moment that we can take for questions and comments.
Okay, so yeah, we have several questions. Paul, do you want me to relay the questions? Do you want to do that?
Yeah, you can do that.
Okay.
If you want. I actually have two questions based on this myself, so I'll be asking questions.
Okay, So let's let me just mention this. What does open access to educational resources look like, and how do these resources work with the other points? As an example, open source code without usable documentation isn't very open as an educational resource.
Right. Yeah, this is a good question. So there's been some work in the research software engineering community to create resources that are available under a Creative Commons license so that anyone can use them with attribution. And these end up being things like ebooks that you can go to a website and read. So there's one called Research Software Engineering with Python. And I'll try to remember to post the link for that. But that one goes through pretty much all the things that, all the essentials that you need to contribute to an open source project. So using Git and GitHub, the Unix shell and Python, and also things like best practices. In terms of plasma science, we could have things like Jupyter notebooks, educational notebooks that use, for example, open source software to introduce different concepts for plasma science. And these are only some of the examples, and there are a lot more that I'm not aware of. So that's a good thing to look up also.
Thank you. Then we have another question. Does the toxic culture of plasma science exceed the levels of other fields, for example, other physics or computer science, mathematics?
My own experience has been, like, I've gone back and forth between astronomy, solar physics, and fundamental plasma science. And in that respect, the further away you get from Earth, the less toxic the culture is. So plasma science has more toxicity in the culture, in my own experience, than the other fields that I've been a part of. And it's something that, as a community, we really need to work on.
Paul, do you want to go ahead and ask one of your questions?
Yes.
I see you
I have a
thrilling.
question. I have a question and a comment. The question is, so I have had your pressure to publish. I actually interact with Chinese colleagues through collaborations quite a lot. And I was surprised to find out that graduate students at the institute where I go, a condition of getting a PhD is they have to have 2 high quality publications. I see Christina nodding her head because she collaborates also. And I think this results in not good papers being published, or papers being published that have too much duplication between them. Have you seen this at other places as a being, I mean, as an educator, I do not think that that's a good, I would not hold that over my graduate students, that they need to publish 2 high quality papers. You always hope they're going to publish at least 1 paper, but so I was wondering what you thought of that.
Yeah, that's interesting. I'm not a fan of the one-size-fits-all approach to graduate education. And if someone has 1 paper that they spend a lot of time on, or 1 project, there should be a way to proceed forward with that. And I don't even think that a thesis is necessarily what should be considered. If someone has, for example, a really nice piece of scientific software that they spent their thesis developing, then maybe that would be good enough for a PhD in research software engineering. So it's complicated, and I think I have more opinions on this than I have time for right now. But I think there are yeah, so I'll
I think
stop
it's
with that.
generally a bad idea, a bad requirement that's problematic. Let me just,
Well, it puts a lot of pressure also on the students and
Yeah.
to perform according to certain standards. And yeah, and I agree with you, Paul, that definitely leads to rush the publications and might carry, yeah, it might be incomplete or would not be as good as if students had more free and creative time to work on it. I definitely agree with that. Marisa commented that many individual groups do actually hold the standards, so not just in China, I guess, but also in the US. So
the other, I just have a brief comment. After being in plasma physics since 1977, when I started graduate school, I think your pyramid that shows psychological safety is the #1 sort of fundamental thing is absolutely accurate based on my experience. That's all I'll say. It's the
Okay.
fundamental problem in the fundamental area where things need to be shored up and yeah, okay.
Yeah, and going back a moment, the paper for that was by Kimberly Young McLear et al. So yeah, I do recommend going back to that.
mhm.
And my slides are on Discord and
Yeah.
Dropbox and Zenodo, a bunch of places now. So
I
All
have
right.
another couple of questions from Discord. If we have time for more questions, Nick, can I?
Oh, sure.
So what if a student is already in a toxic culture? What he or she can do for that?
Oh, that is tough.
So there
The
should
first,
be in place already some kind of, tools, right? Every institution might have this channels for report toxicity or support, right? That's one thing.
yeah, every institution should have a humans relation code and a bias incident reporting policy. And I think finding supportive plasma scientists outside of the group and working with them to maybe find a different group to work in. This is something that does depends strongly on the situation. But a lot of times it's been reaching out to other members of the community who are a lot more supportive, who are able to navigate the bureaucracy and that sort of thing. But I don't think that my answer is quite satisfactory. There's a lot more to this than that.
Okay, yeah, and we have, well, it's a complicated topic. I think it's not always true that you can really change, research group if it's a toxic environment. And it's going back to your slides. It's really a question of changing the culture and making the environment, less toxic and non-toxic by default. And yeah, we have a question from Greg. How does research from private corporations fit into this in terms of IP concerns and similar? It seems like that's anti-ethical to open science, but also that there is a lot of good research that comes out of private corporations.
That is a good question. There are times where it is really advantageous for private corporations to engage in open science. And one example is open source software. So if there's particular software that a company really depends on, and they make it open source and they build up a developer community, then they'll be able to spend less on the maintenance for that. But there are other times where it would be disadvantageous for them. And with capitalism, the there are conflicts with the open science paradigm, but there are places where they can go really well together.
Thank you, Nick. I think we can go ahead now, and I'll, yeah, we can just take the next slot for more questions that are coming in, actually. So.
Oh, okay. I'm happy to have a lot of discussion. And I don't have to get through all of my slides anyway. So.
Did we cover the question by, I was looking on Discord, Jose Morales? Who's that?
Jose just wrote, no, I didn't relay that. You want to?
Yeah, so he has there's also a question of environment. Ideally, code written now should be executable in 20 plus years. How can we ensure that these programs will run in 20 plus years? In Europe, well, wait a minute. Yeah, in Europe, ideally without, I'm sorry. How can we ensure that these codes will run in 20 plus years? Wait, I'm reading the wrong thing. No, I know, I'm not. Okay. And ideally without having to rely on obscure VM configurations, compiler settings, et cetera, et cetera. And there was a reply that Docker is great for this in my experience. So how would you say, so again, the question is, ideally, how do you make code written now be executable in 20 plus years? That's like the ultimate portability and et cetera issue. How can we ensure that's happening? Yeah, go ahead. I'm curious to hear your answer.
Yeah,
you can answer to that too, Paul, because I guess you wrote some code 20 years ago, right?
Indeed, I did.
Yeah, I think containerization is one of the big things that we can do. So things like Docker. One caveat is that Docker files from maybe 5 years ago, do they still work today? And I haven't used Docker that much, so I don't know. But there are other efforts. The only one I can think of right now is called reproducible, which do try to record what the software that was used was. But yeah, so yeah, things like containerization and are probably the way to go, but also recording which versions of software you need.
Don't you think, Nick, that that's kind of, that's a very broad, difficult question, though. Maybe some codes that were written 20 years ago, you don't want to run now. Or you might want to take from them the algorithms. Some of the code that was written many years ago or decades ago have algorithms in them that work extremely well, and you always want to preserve that. But maybe you don't want it running under Fortran 77. You would prefer to run it under, whatever, C++, or Fortran 90. So I think the answer is kind of complicated, yeah, that maybe the best thing isn't just to be able to take a code and run it 20 years later. It's like a process that's constantly changing. I don't know.
Yeah. One practice that I do recommend is making source code and data used for projects available on Zenodo, which is an online archival website, and that will preserve the data for probably at least decades. So that is one of the main ways that we can ensure that software source code still exists in a couple decades. And then often there will need to be some additional work to make sure that it runs in the new environment. So, all right, I think I should move on. Yeah, these are great questions. I wanted to go through a case study comparing solar physics to fusion energy sciences. And there are some similarities between solar physics and fusion energy. Plasma physics is foundational to both. There are a lot of the same diagnostics that are different, and especially for different regimes. And there are a lot of comparisons between simulations and reality. But there are some differences. solar observations tend to be more homogeneous. There tend to be images of the sun at different wavelengths, a lot of spectral measurements, and then time series. In solar physics, we also don't have any experimental control, really. And one point that was brought up to me when I first went through this is that there's only one sun, to which I countered that we don't often launch tokamaks into space. So there are different complications for each of these fields. So for the solar physics software environment, there are two main components to that. The first is SolarSoft, which is a community developed package that has been developed since the early to mid 1990s. It's written in IDL, which is a proprietary language, and also SolarSoft doesn't really have clear licensing. SolarSoft is also pretty monolithic in architecture, so it has analysis code for a whole bunch of different solar missions. So solar physics does have a history of community software development. In the last 10 years or so, there's also been SunPy, which is a community developed open source package since 2011 or so. It's written in Python, which is my favorite open source language, and it has a much more modular architecture. And it's also written using modern research software engineering best practices. So things like making sure that everything is really well documented and having continuous integration testing and all sorts of things like that. For the solar data environment, one big difference with fusion energy is that most observational data sets are openly available. And the main way to access that is through the virtual solar observatory. And what VSO does is it allows us to simultaneously search databases for a whole bunch of different instruments, and then be able to download data from a whole bunch of different sources, a whole bunch of different observatories. And there are multiple ways that we're able to use VSO. We can use it through a web interface. There are ways to access it through SolarSoft. And we're also able to access it through SunPy. And it's important that metadata from solar physics and space physics are somewhat standardized. They're not perfectly standardized, and that causes problems, but there are a lot of keywords that are used in common between different missions. And because of the Virtual Solar Observatory, if I wanted to download the data from my favorite solar flare, I could start doing that in a couple of minutes and then use SunPy to load the images in another couple of minutes, and then be able to get images that are maybe not this quality that quickly, but you can do quick looks of the data. So accessing data in solar physics is really straightforward. And there are some consequences. The data sets that have come into existence are widely used and reused, and multiple groups can study the same event. And it's customary to use data from multiple sources. Because data is moderately well standardized, they're better suited for machine learning studies. And the software tends to be pretty well documented and also well tested. Because software has been developed in the open, there's a lot less duplication. And data access has not been restricted by major institutions. In contrast, the fusion energy sciences data environment, access to most experimental data is restricted in some way, though we can often request permission and submit a user agreement form that we end up signing. But these user agreement forms often contain restrictions, like limiting them to users can't use them for commercial purposes. I was going to sell t-shirts with D3D data, but I guess I'm not able to. But sometimes you might be able to do that with prior approval. And these user agreements also restrict redistribution of data, again, without prior approval. And then there's often an internal approval process required for presentations and papers. For fusion energy sciences, also the metadata are less standardized than in solar physics. And because the data tends to be closed access, it's difficult to search across multiple archives. For the software environment, there's a dependence on legacy codes, which are often closed source. And legacy codes tend to have different degrees of documentation, testing, and usability. Though I should say that a lot of software and data sets are bridged together by OMFIT, which is happily supposedly going to become open source soon. They have a couple of things that they still need to do before that happens, but they're working on it. And this is also something that we're not there yet for Plasma Pi, but we are working on it. Software license also tend to be customized. And again, there are restrictions on commercial use and limits on redistribution rights. And that makes it difficult to figure out what codes are out there and what the different codes end up doing. So there are some consequences. In fusion energy sciences, it's harder to find data, in particular because we can't simultaneously search across multiple data archives for different tokamaks or other fusion devices. It's hard to access data because we need to request permissions, and that makes it difficult to perform cross-device studies. And also the lack of standardization makes it hard to write analysis software for multiple devices. But the need is being partially met by OMFIT. And again, we're working on that for Plasma Pi. And a bigger consequence is that there's reduced scientific reproducibility. So in the sense of being able to reduce the results given the same original data. But the situation is changing. There's an increasing number of open source software projects in fusion energy sciences and plasma science. And that is something that does make me optimistic for the future. We did hear about a lot of these in the Plasma Hack Week. So I built in a 3-minute break here. And I'm also happy to take a few questions. So feel free to get up and stretch, and I'll be around for anyone who wants to ask anything.
Okay, thanks. I don't see any questions, Christina, in the Discord window right now.
No, no. There was some interaction about Zenodo, but no, I don't see any additional questions, so we can take the break. And
that's a good point, actually. That's a really good point. The more you document up front and warnings, caveats, that's a huge help.
Yes, it is. All right. I'm a little behind schedule, so I might skip a few things, but the next topic is the FAIR principles for data stewardship. And FAIR stands for findability, accessibility, interoperability, and reusability. So what findability means is, well, before we are able to reuse a data set, we have to be able to find it. And doing that, the best way to do that is to assign different digital resources a persistent identifier. And most often this takes the form of a digital object identifier, or DOI, which we often see for papers, but can also be used for data sets and software and this presentation, I uploaded it to Zenodo, so it has a DOI also. But that makes it a lot more citable and able to be found. It's also important to describe data sets with rich metadata, and that lets us index data sets in a searchable resource. And what we talked about a bit before is Zenodo, which is one of my favorites. And then the Virtual Solar Observatory was also an example for that. Accessibility means that we can access a data set using its persistent identifier. And when the data is gone, we're still able to access the metadata. One nuance is that accessible does not mean open necessarily. And sometimes for really good reasons, authentication and authorization are required. So if working with medical data or social science data, it's really important to be careful about patients' privacy rights. So it's important to have these in there also. But one of my main points for today is that data and metadata should be openly available when possible. So data sets from most Fusion devices are not openly available. And the question is, how do we address that? Should each device create its own online open archive? And the problem with this is that it could lead to duplication of effort and potentially limit cross-device searchability. But what if we create a community-wide portal to access Open Fusion and Plasma data sets? And that's something that would improve findability, accessibility, and reproducibility. And it'd make it a lot easier to enable cross-device studies and allow much wider reuse of data. So kind of along the lines of what we're talking about before is a concern that often gets brought up is making sure that data or software gets used as it's supposed to be used, make sure that it gets interpreted correctly. And there are a lot of ways that we can go about doing this. So releasing the analysis techniques, algorithms as open source software is one. Providing a data analysis guide that can include things like Jupyter notebooks that go through the different steps to, say, calibrate data, and then things you can do to interpret the data. And in the data analysis guide, it's important to include admonitions, warnings about potential misinterpretations of the data. So making sure that a particular density diagnostic is only used in a specific parameter regime. And warnings can also be included in the code also. In the solar physics community, it has also been really common to hold tutorials on data usage and also software at conferences. And one thing that has been done somewhat less is posting tutorials, recording tutorials on how to use the data or software on YouTube or Zenodo. When we have a data set, it's important to include rich metadata. And we can also flag untrustworthy data. I did also want to say that some data from the mega ampere spherical tokamak is now openly downloadable from the internet. So I think I linked to this from the graphic in the presentation slides, but you can get to a bunch of different experimental results from MAST. So if you're interested in carbon dioxide interferometry, you can find these open data sets. So that is an important step in the right direction, I would say. It's also important to make data interoperable. So fusion facilities tend to have their own way of storing and organizing data. And this doesn't it's not so important the format that it's in. So it's okay if it's HDF5 or MDS plus, but the different terms need to mean the same thing across different devices. And because of this, it's harder to perform cross-device studies and harder to develop shared software. There are a couple of different approaches. We can develop software to serve as an interface, and this is the approach that OMFIT has taken and has done well with. And the other approach is to adopt shared standards for data. So why do we need data interoperability? So suppose we're doing experiments at two facilities. So BAPSIF, Basic Plasma Science Facility, and Wisconsin Plasma Physics Laboratory, or WPL. We're studying the same physical process, but data from BAPSIF and WPL are structured differently, which means that we need to write separate software to perform the same analysis. On the other hand, if we had a common data model for these different facilities, we'd be able to share in the development of software and promote more cross-device collaborations. There are a few examples in plasma science of these common data models. So IMAS, Plasma MDS, OpenPMD, which is for particle and cell simulations, SPACE, which is for space data, and then Metasat, which is a metadata standard for smallsat and CubeSats. So plasma science needs open metadata standards. There's a reason why singing about them is one of my hobbies. A metadata standard is an agreed upon way to structure and understand data. In a metadata standard, you assign a meaning to each variable name. And you do that in order to reduce ambiguity. Having a metadata standard and following it greatly improves interoperability, which in turn allows different groups to use and interpret data. And if you have multiple metadata standards, you can develop a metadata crosswalk to convert between the different standards. All right. So why should metadata standards be open? There are some standards like IMAS for ITER, which are not open. When we have open standards, that allows for wider adoption. And some really big examples of that are PDF, Blu-ray, and so on. But when we restrict access to standards, that limits their adoption. I don't know how many of you remember Betamax, but it was a competitor to VHS back in the early 1980s. And while VHS allowed other companies to use their format, Betamax was a lot more restrictive about it. And for that reason and other reasons, VHS ended up winning out over Betamax. So it is important to make sure that standards are open.
Nick, can you take a question right now? Somebody raised a hand, Greg Wallace.
Sure.
He had I don't know if you want me to interrupt like this. I know you said you had set times, but.
Oh, now's a good time.
Okay, Greg, can you go ahead?
Hi, thanks. I have a question. You referred to ITER as a not open or perhaps closed standard. I can't remember the exact word that you used, but can you explain exactly what you mean by it not being open? Because, for example, IMAS is now being used across a number of tokamaks in Europe. They've adopted IMAS as their, data sharing standard. So,
yes, yes, that is an important point. So, in order to access IMAS, you have to be a member of ITER, essentially, or potentially get participation from that. But if you go onto the ITER website, and you have to log in to be able to access IMAS. However, I should point out that there is a Python package, OMAS, O-M-A-S, which does provide an interface in Python for IMS data sets. So the situation is less bleak than I made it seem. So, but if you want devices that beyond tokamaks in Europe, for example, it'd be really helpful to make that standard open so that you can download it from the internet without having to log in. All right. Let's see. For reusability, we want to be able to describe data with sufficient metadata and make sure that the metadata meets community standards. We also want to make sure that data sets have a clear license, and often that would be a Creative Commons license that allows reuse and redistribution. Data sets should also include metadata that describes the provenance. Where did the data come from? And the benefits of reusable data are that it broadens access to research data, maximizes the knowledge that we can gain from different data sets. Again, it improves scientific reproducibility and enables machine learning studies. There has been an effort in Europe over the last 2 or so years called Fair for Fusion. And the goal of Fair for Fusion is to make EU-funded fusion data more widely available and findable, accessible, interoperable, and reusable. They're also working to raise awareness of open data within the fusion program and develop tools needed for an open data approach to fusion. And they also want to lay the foundations for an open data policy. And we'll go through that. So there are a lot of different aspects to findability, accessibility, interoperability, and reusability. And the current status, most of the requirements are not being met by the fusion community. But Fair for Fusion is hoping to get things like rich metadata and persistent identifiers and things like that to improve the situation for fusion energy science. But one lesson that they've shared is that it's difficult to change an established community with what we think of as working practices, but there are other communities that show that it can be done. So I think, given the time, I will wait till the end for questions and move on to open source software. So,
Nick,
go ahead.
there was a question in the chat window that may be already answered through the last several slides. Can you elaborate about standards for data and fusion? Is there a leading effort in this area? I think more or less covered that, did you not?
I think IMS is probably the leading standard for at least tokamaks. I've asked questions about if it's applicable to stellarators and other devices. But it is the leading one. But there are some for subsets of plasma research, like OpenPMD for particle and cell simulations, describing the output from that. And that's being used by a bunch of different particle and cell codes. All right. So software is open source if anyone is free to use it, modify it, or redistribute it. And according to the open source definition, which is from the open source initiative, an open source license cannot discriminate against any persons, groups, or fields of endeavor. So if a license has restrictions on commercial use, it's not open source. And if you want to go to a list of approved licenses, the open source initiative is the best place to do that. And it's important to note that customizing licenses can lead to unexpected problems, like losing compatibility with the open source definition, for example, but also making it so that your code can't be used by certain other projects because of license incompatibilities. All right, so most of us, if we're attending this summer school, we've used scientific software, and there are a lot of pain points that show up with it. There's often a lack of user friendliness. A lot of the codes that I've used have been difficult to compile and install. There's often, not always, inadequate documentation. Sometimes the code is unreadable. There can be cryptic error messages that you have to be a user of the code to be able to understand, or developer of the code. There are also licensing issues, and packages tend not to be written to work well with each other. And a lot of code is also unvalidated. And the reason why, one of the main reasons why this has come about is through what I'm calling publication-driven development. And in academia, it is unfortunately common to measure worth by the number of publications. This is bad. Because of that, we end up writing code in a rush to get papers published, and we give low priority to user friendliness. And there's more of an emphasis on writing papers instead of things like documentation and tests. Overall, software isn't really valued as a research product. And the funding model situation is changing now, but there's a tendency to fund research projects, not infrastructure and maintenance of different software packages. So those get lower priority. And we also tend to avoid hiring, or we just tend not to hire software engineers. And what all this leads to is a buildup of technical debt, where technical debt is the consequences of making a quick fix to get results now, rather than making a more thorough fix in order to have better code that works well into the future. So publication-driven development is one of the reasons why we end up with legacy code. The consequences of these pain points are that it's hard to begin research, it's hard to collaborate. We have not only duplication of functionality, but also triplication and quadruplication. Research is less reproducible. And in my experience, research can become really frustrating. But we can address these pain points by making our software open source, by taking care to write readable, usable, and maintainable code. We want to be able to use a high-level language like Python or Julia when we can. Make sure to prioritize documentation, make sure that we have an automated test suite, and then change our model so that instead of developing code in as parts of separate groups, developing code as the overall community. And we want to be able to build a shared software framework, or it's also called a software ecosystem. And that is the goal of PlasmaPi, which is an open source project with the goal of growing an open source software ecosystem for plasma research and education, where a software ecosystem is a collection of software tools that are developed together and grow together in the same overall software system. And there are a lot of ways to be part of the community. We have a community meeting each week that's open, as well as office hours. We have a chat room. It's really helpful to request new features on GitHub and organize community events, and also to contribute. This year, we also had the first Plasma Hack Week. A lot of PlasmaPi people were organizing it, but there were a lot of people from the broader Plasma community. So it was a big community effort. And a Hack Week is a mix of a summer school and a hackathon, though this year it ended up being more on the summer school part of the spectrum. There are tutorials. We had tutorials for research software engineering, so Git and GitHub, how to use different Python packages for, or software packages for plasma science, going through how to contribute to open source projects, how to write clean scientific code, how to test scientific software. And we also had tutorials for different plasma packages, including some pretty nice ones. The videos should be posted online soon. We're a bit late at this. It's taken a bit more time and we've had too many other things going on, but we're hoping that this will become an annual event. And to go through this fairly quickly, we have several current and planned PlasmaPi subpackages. Our particle subpackage describes or includes object-oriented representations of different particles and plasmas. Our formulary includes calculation of plasma parameters and things like transport coefficients. It only took us a year and a half to think of that name, but it works pretty well. We're starting to develop a simulation subpackage, which so far includes a particle tracker that is undergoing some refactoring right now. We have the analysis and diagnostic subpackages, which are to analyze data from simulations and experiments and observations, and also to represent and work with results from different plasma diagnostics. So things like swept Langmuir probes, Thomson scattering, and very recently, Peter Hoyer added some charged particle radiography, proton radiography functionality, which is really helpful for high energy density plasmas. And a few students at the University of Delaware have been working on various dispersion relation functionality for plasma waves. Then I'll skip that. But there are a lot of challenges that we're facing. The biggest one is changing the culture, because we need to get to where we have community-wide collaborative software development. This has been done in astronomy with AstroPi, in solar physics with SunPi, and with a whole bunch of different packages for different fields. Building community is vital to this. The community is more important than the software. And an important component of that is to support new contributors. And one thing we're doing now is revamping the contributor guide. There are also some technical challenges, like the lack of a community-wide portal for experimental data. And then again, the lack of open metadata standards. All right, and I will skip this, or pretty much say that research software engineering is a new field for people who are in between researchers and software engineers. And the US Research Software Engineer Association is a place to go to learn more about that. And so for a summary, plasma science is gradually becoming more open. If we want to get to open science, we need cultural change, institutional change, and technical infrastructure. Scientific data should be findable, accessible, interoperable, and reusable or fair. And work is underway on an open source software ecosystem for plasma research and education, which is centered around PlasmaPi. And with that, I'm happy to take questions, and I'm surprised that I finished at the time that I was hoping to.
Thank you very much, Nick. That was really a great talk. I really loved it. Thank you so much. I don't see any questions in the chat window. There was a comment by Jose Morales saying perhaps a yearly publication or blog on the state of different codes and software would be helpful.
Yes.
It would be an effort, but it would be good if someone did it.
One thing that we've started to do on PlasmaPi's webpage is to list different software packages for that are in use in plasma science. We still have a lot of work to do to get everything that's out there, but we have a couple on there already, and hopefully we'll be able to add more to that. So if you have software packages that should be added, you can go to the, well, talk to me on the Discord channel and I can point you to the repository. Yeah, that's a good comment.
And if people want to just open their mics and ask a question on the Zoom, they can do that. It's good to put the question in Discord though, because we have a record of it and people can see it. Let me just check Discord again.
On Discord, I also posted a scheduling link near the beginning that if any of you would like to talk more about Plasma Pi or Open Plasma Science or Open Metadata Standards, we can feel free to pick a time on that link and it'll automate adding a calendar event and generating a Zoom link.
I see it. Let me see. We should give people a few minutes to think if they have a question to type in or they want to just open their mic. You don't have to raise your hand.
I may just ask the question that I just wrote on Discord. I'm getting a lot of noise. Can you hear me well?
Yes, we can hear you well.
Okay. I was wondering if you think that the common practice in machine learning, in the machine learning community and other communities to publish work on personal blogs, do you think that's a healthy practice to keep updates very open, or do you find that to possibly fire back in some way?
I'd say it has advantages and disadvantages. It allows the results to be communicated quickly. It won't necessarily be seen by as many people. And it doesn't have peer review, but I think if it's working for the data science community, then I think that's the most important thing. But there are pros and cons, I would say.
I think one of the biggest cons, Francesco, is this big issue of peer review or, just like on some computer systems like NERSC, you can't get a computer account unless if you give a personal Gmail address or something like this as your email address. It has to be some affiliation with the institution. So the officiality part is always a good thing sometimes. I don't know.
Yeah, the downside of that is the speed, as Nick was saying.
Sure. That's a trade-off.
You can publish on a blog within a day, but to put things in a paper, we tend to over polish things at times.
Yeah.
And when we talk about open software, the point of making it open is for others to use it. And if they don't know what it is, there is a downside. I guess this is related to what Nick was describing as publication driven. Don't remember what was the last word, but we shouldn't really prioritize the papers, maybe.
I would less emphasis on the papers. I also tend to think that journal articles aren't really that good at communicating scientific results. And there can be ways that are more effective at communicating. Like I tend to learn best by going through a set of slides, for example. But I think like the publication practices that we have now haven't changed as much as they probably should from a few decades ago.
Are there other questions? I tend to rely on publications related to a code or numerical simulation results. The only thing I think that persists over decades is not the code that was written, but the physics results from the code. And I think that's where the publication is useful. The peer-reviewed publication is useful for archiving that. And you can almost use that as a way to verify a rewrite of the code in the future. Something.
Yeah. one comment on that is that the practice of citing a research paper on a code as a proxy for citing the code, an analogy that I've heard is that that's kind of like if you want to find an article on, if you want to find Moby Dick, the book, you don't want to get a book report on Moby Dick. So citing the code directly, putting code on Zenodo, getting it a persistent identifier, and then using the persistent identifier in the references for a journal article. That's the emerging best practice for software
It's a
citation.
fair point. I agree with you. It's a fair point. Very fair point. Point well taken.
I'll try to remember to post an article on Discord by the librarian where I work, who went through this in a lot of detail in a paper recently.
Are there other questions? Let's see anything more in Discord.
Yeah, please feel free to take a break when you need to.
So what I said about publications is really it's grounded heavily in the way I was trained, you see, from the decades ago of the 1970s. And that's how people were trained to think about publishing out codes. You make a fair point.
It's a practice that's been changing. And a lot of people across the scientific community have been working to develop software citation best practices. And I don't think they're done yet. But yeah, I'll try to post some resources on Discord.